Okay, welcome everyone. My name is Vic Sparrow, and today we're going to talk a little bit about the recent activities in the Center for Acoustics and Vibration, Propagation and Radiation group. Hope that you're all having a great day, and thank you so much for tuning in. And you should be able to see me now. Hi everybody, thanks for joining. So the Propagation and Radiation group has several faculty members who are associated with it. A couple of them are joining me today. The group includes Anthony Atchley, Tom Gabrielson, Peter Newman, and we're joined today by Steve Thompson and Michelle Vigeant. And basically, as you know, faculty have the fortunate opportunity to work with a number of great graduate students. And we have a number of Master's of Science and PhD students in the Propagation and Radiation group. And as you know, the students do a lot of the work. And so we're just here to touch on some of the highlights for going this year. What are some of the things which are going on? There simply is no way we can go through all the projects and things that are ongoing. So this year we're going to focus on 3 highlights. Dr. Vigeant's going to give you a preview of some of the research going on in her lab and a tour that's going to be available as part of the CAV workshop this year. Dr. Steve Thompson is going to be talking a little bit about moving coil modeling. And I'm going to round things out and talk a little bit about a special project funded by NASA we've completed here at Penn State called the SonicBAT project. So without further ado, I want to turn things over to Dr. Vigeant, and she can give you a preview.
Thank you, Vic. So I will just briefly talk about the research I do and preview of the lab tour. So the overarching research theme that we do in the Sound Perception and Room Acoustics Laboratory is trying to quantify human response to acoustics. So we have some general goal of good acoustics for interior spaces, or also people living in their homes and their exposure to environmental noise. And we want to know the human response to that. With environmental noise, it might be annoyance. With interior acoustics, it could be the perception of how good speech intelligibility is, or how reverberant a space is for music. And we want to be able to connect these with metrics, values that we can quantify about a sound field. And so we do subjective work to relate the two, so that then we can have specific metrics to design spaces. So in the tour, I'll talk more about some recent projects that we've been doing. The work that we do is primarily with virtual acoustic reproduction, and we use the oralization and reproduction of acoustic sound fields, or the ORIS facility. We use a method of ambisonic reproduction, which will be discussed. This facility has 30 loudspeakers arranged in rings, with 8 below the central listening position, 12 at ear level, 8 above at plus 30 degrees, and then 2 nearly overhead at 60 degrees. And then we have subwoofers for reproducing low frequency content from, for example, aircraft noise. So more details about the work we've been doing and this tour of the space, including a video, will be presented on Tuesday, the 27th.
Okay, thank you very much, Dr. Vigeant, for that. We look forward to the tour. I'm going to encourage everybody to take a look at that, and please participate as you are able. Okay, so next we are going to talk with Dr. Steve Thompson about some of his moving coil loudspeaker work. Dr. Thompson, would you like to go ahead and show your slides?
Okay, can you see them? Actually, you're probably seeing the wrong screen.
We're seeing a different screen.
Let me share it differently then.
No problem.
Now you're seeing the right one, I think.
Okay, go ahead, please.
Okay, so this is some information on sharing, on modeling moving coil speakers, including the nonlinearities in the speakers using Simscape. Simscape is a product of the MathWorks, the people who make MATLAB. And we're actually in discussion with them about possibly funding a little bit of this. We'll see if that actually works out. But why am I not advancing there? The speaker that I'm going to talk about in detail is this this is actually a 3.5-inch wideband full range speaker, it's called. It's got a resonance frequency of about 100 hertz and goes up to about 15 kilohertz with reasonable fidelity. It's again a 3.5-inch speaker. These are little boxes that I built that sit on top of my TV, and we've got a bunch of these things also in the lab. Looking in more detail at how we're going to do the modeling. Basically, a speaker is a moving cone, which acts as a mass being driven by the magnetic forces in the magnetic loop here. This would be a ferrite magnet in this case, with the flux moving along the axis of the speaker. These darker pieces here are high permeability magnetic structures, so that the flux circulates in this direction. This is an axially symmetric picture here, so the flux goes like this, and is going through the gap, across the gap, where the coil moves along the axis in the gap. If you put a current in the coil, that creates a force along the axis that drives the speaker. So we have the mass of the speaker, which is mounted in a mechanical structure that has a restoring force caused by the suspension, both the spider and the outer suspension here. And the driving force comes from the magnetic structure. Speakers are in all different sizes. The one that I've shown you is 3.5 inches. Speakers of that design go up to perhaps 24 inches maybe. These are much smaller speakers that would go into a headphone or an earphone. This is an inch or so in diameter. This one is about a half a centimeter in diameter. These moving coil speakers come in all sizes. The conventional model that's been used for decades for modeling these things treats the electrical components, the resistance and inductance of the coil, coupled to the mechanical components, which are the mass, stiffness, and resistance in the mechanical domain, which then coupled through the to the acoustical domain by the area of the loudspeaker to radiate or to include things in the back volume. Bring that back up. The equation that relates the electrical to the mechanical domain is here. That's represented by a gyrator in the electrical circuit, and the transformation between mechanical and acoustical domains is simply multiplied by the area. So these are the equations that need to be implemented. When we move that to Simscape, now this is essentially the same model as before, at least almost. Simscape uses the modeling variables are velocity and force in the as a mobility domain. So you need to keep that in mind, but basically it's the same model with electrical domain, mechanical domain, acoustical domain, and then coupling components that take the signals from one domain to the other. So again, same equations would relate the electrical and mechanical domains and the mechanical and acoustical domains, same equations as before. If we're going to include nonlinearities, this is where it really becomes interesting. Now, for example, one of them is that the electromechanical coupling becomes a nonlinear function. Now, BL is a function of the position And that can be measured. This is measured by a clippable measurement system that I'll talk a little bit more about using, and the clippable measurement system gives you the power series coefficients for expanding that into a power series. Likewise, for the nonlinearities and the mounting compliance, it's possible to measure that nonlinearity where this K of X, K depends on the displacement of the cone from equilibrium. Again, do that as a power series expansion to put that into the value of the component in order to be able to deal with the nonlinearities in some way in the circuit. Now, if we're including nonlinearities, we have to do this in the time domain. The frequency domain only works for linear time invariant systems, so we have to do these things in the time domain. Simscape works primarily in the time domain, so that's not an issue. You can go ahead and run this model, but are you going to believe it? How do you know if the values you're getting make any sense? Well, we have the ability to do these measurements and see if our calculations are making any sense in comparing with the measurement. We were lucky this year to receive an anonymous donation to buy a clippable measurement system. This is a system that is widely used in commercial industry for making this kind of measurement. And the measurements that I showed you earlier were actually made with this test system. The waveform that I'm going to show you is an interesting one that shows an awful lot of data all at the same time. This is a multi-tone signal where you can see we've done an FFT to show the components here. We put a big handful of frequency components in this signal. These are all arranged to be at the bin centers for the FFT, so that we're doing we don't have any scalloping or windowing, don't need to do windowing to get these things. But what's interesting about the way this is done is that we put quite a number of tones in, but we also leave a large number of empty bins for reasons that I'll get to in just a minute. Now, doing all of that might normally give you a signal which has an almost indeterminate crest factor. But if you're very careful about choosing the phases for all of those things, you can get a signal whose crest factor turns out to be very well controlled. This looks noise-like, it sounds noise-like, but in fact, it's a completely determinate signal whose spectrum you know very well. And it's a very nice signal for doing this kind of testing. One of the things that you can do is to use the empty bins. The empty frequency bins should be 0 if there is no noise or distortion in the system. But the first thing you can do is to measure the noise level in the system. And the clippable system does this by starting out doing a measurement with no input signal to find out what the noise level is in the bins. I've shown here a very low noise level, but the noise level is showing up in the empty bins, so you can see where the noise level is. Now, if we do that measurement for this speaker, and I'm going to concentrate on this one in the bottom right corner, what we see here with that measurement system is the purple, the color, this is the measured displacement of the cone as a function of frequency. At each of the individual components, we can see that it's flat at low frequencies, that the resonance frequency of the speaker starts to fall off at 12 dB per octave. The black is the noise level in that signal that was measured first with no input signal, so we can understand where the noise floor is. The gray now, these are the signals in the empty bins that include both noise and distortion. So we can get a measure of the signal, the noise in the measurement, and the additional signal that comes in through the distortion. So we have a measure of distortion. This is with a very low level signal. Notice that there are several, 4 or 5 orders of magnitude between the expected signal and the distortion here for a low drive level. If I increase that drive level by, I think this is about a 30 dB increase in drive level up to something that would be about 20 dB below the power limit of the speaker. Now the distortion has started to increase significantly, not to be too high. We've still got a distortion level that's a couple of orders of magnitude below the signal, but we can see that it's coming up. This is in a measurement. We have the ability to do this in this measurement in our model as well. So in the model, the noise level is actually just computational noise. And we can see that this is done with the linear model. The computational noise is really very small. If I do that with an input signal in the nonlinear model, we get a noise level which is, we get a noise plus distortion level that is, again, several orders of magnitude down for a small signal. As we increase the level of that signal, now our distortion plus noise level, which is now mostly distortion, is starting to increase and becomes very much more, as we get to high levels of drive, it becomes fairly significant. So the model has the ability to do this kind of calculation, and I'm going to just zip ahead because I think I'm running out of time. But we have the ability to do that level of detail in our measurement with nonlinearities, and to be able to package this thing up into a component. We can have a linear speaker or a nonlinear speaker in here and be able to put this into more complicated systems. So this is the kind of thing that we can do with this modeling system. And as I said, the ability to do this kind of thing is something that I think the MathWorks is interested in encouraging, and I hope they encourage us to keep doing it. So thank you. I would be happy to talk to any of you about this afterwards, but we can let it go at that. Thank you.
All right, Dr. Thompson, thank you again very much. That's a really impressive capability, and it's good to let our industrial liaisons and government liaisons be aware of that capability. So again, thank you very much for being with us today. I greatly appreciate it.
Thank you.
So I'm going to go back and show my screen. And now we're at the point where we were before. We've now heard from Dr. Vigeant and Dr. Thompson. Now it's time for me to talk a little bit about something going on in the SonicBAT project. So I'll go ahead and move on to that. So about a year ago, made a presentation at the International Congress on Acoustics meeting in Aachen, Germany. So for those of you who are aware of how things work in Europe, more and more people are being encouraged to participate in meetings which are open access. So this is a very high level acoustics meeting, but right on your screen right there is you can get the paper for free. So I'll leave that up for a minute, and you could stop the video if you wanted to write it down, and you can just pull down and get the paper from that conference that we presented for free. But what you can't get on the conference are, in fact, the slides. So let me go ahead and pull up the slides for that meeting. And just give me one moment, and I will pull up those slides. And I'd like to thank my co-authors on this. I won't go through every one of the slides, but I'll go through most of them. So I'll tell you a little bit about what the SonicBAT project was, how we at Penn State were involved. First of all, I'd like to thank the major graduate student who worked on this project, Dr. Trevor Stout. He graduated in December of 2019, and he's now employed at the Johns Hopkins Applied Physics Laboratory. I'd also like to thank Kevin Bradley and Christopher Hobbs, who were both very involved from this on this project from Wiley Laboratories, now called KBR Wiley. And since that time, Chris has now moved to a new position with the Federal Aviation Administration. So again, we're all going in different directions, but it was a very fun job to work on. Overall, the SonicBAT project was a collaboration from a number of different people, just Penn State and KBR, but also we were funded by NASA. And there were a lot of other SonicBAT team members, including Lockheed Martin, Boeing, Eagle and Aerodox, TV Systems, Gulfstream, and École Centrale de Lyon. So we are representing and trying to understand what's going on with the return of civil supersonic aircraft. In the past, we had the Concorde aircraft flying over the Atlantic Ocean. And of course, it's not flying anymore, but very soon, similar to Concorde, there are aircraft which are going to be built. And some of the companies interested in building supersonic aircraft include Boom Supersonic and Aerion. And NASA would also like to bring forth new aircraft similar to Concorde, but also much quieter. So there are, NASA is developing the X-59 low boom demonstrator shown in the diagram right here. And that's being built as a contractor by Lockheed Martin, and Gulfstream is also working on low boom supersonic aircraft. And so the idea is that very soon we're going to have civilian supersonic aircraft flying again. So we need to understand it. But you may recall that all supersonic aircraft make sonic booms. So down below here, you can see around the supersonic aircraft, there's a complicated flow field. And because of nonlinear acoustics, by the time that sound makes it down to the ground, it can make a wave shaped like the letter N. That's why we call it an N wave. And that would be made by conventional supersonic aircraft. But up here in the upper right, I'm showing if you take one of those N waves and you compare to what the new shaped booms would be like, first of all, they'd be a lot lower in amplitude and they're much smoother. So they don't sound like boom, boom, they sound like puff, puff. And so there's a lot of research going on in that area. Now, one of the questions that we had is, if you have these supersonic aircraft, as the sonic boom makes it from flying from atmosphere down to the ground, will the sonic boom be affected by atmospheric turbulence? And we know that the N-wave shaped sonic booms are either spiked or rounded because of the effects of the atmosphere. And it's getting to be spiked or rounded because the sound waves are either focusing or defocusing. So if you have a cruise boom signature, which is an N wave, what you can measure from an aircraft on the ground is you see all these different little waveforms. They don't look like N waves anymore. Some of them look quite spiked, or some of them look quite rounded. And this has been well understood for many, many years, that turbulence has this sort of effect on sonic boom signatures. So what we want to do in this particular work is the SonicBAT project meant to look at sonic booms and atmospheric turbulence. Its project began in March of 2015, concluded officially in May 2018. And the final contractor report, well, now it's been another year, has been released. It's on the NASA website. And there have been other work ongoing since the formal end of the project. The formal project was to validate, using flight measurements, models for the propagation of sonic boom signatures through atmospheric turbulence, in an effort to predict the effect of turbulence on the loudness of shaped sonic booms for low boom designs. That is, the shaped signatures, will they be affected by turbulence the same way that the N waves are? So that's what SonicBAT stands for. And of course, we have a little logo for SonicBAT, which involves all the different people working on the project, as well as a demonstration aircraft. This project involved both experiments and simulations. So we did field experiments where they flew a conventional supersonic aircraft, a fighter aircraft, and made measurements. We had to have measurements above and below the turbulence on ground microphones. We needed to do the measurements in both dry atmospheres and wet atmospheres. So for the dry, we picked NASA Armstrong in Edwards, California. And for the wet atmosphere, we were at NASA's Kennedy Space Center down in Florida. And the idea was to get a lot of instrumentation set up and to make measurements both at Edwards and in Florida. We also had multiple simulations in this. There was a classic approach, which was put together by Dr. John Morgenstern at Lockheed Martin, and Trevor Stout's approach from Penn State. Because of time limitations, I'm only going to be talking about Trevor's work, but again, our hats off to John Morgenstern as well for his work. Here's some of the measurements that were made. You can see up above, there's a flight of an aircraft which sort of comes in at a certain height, and you can see on the ground where the sonic boom would be heard. So there's, if we blow up a little section right here, there's an array where a linear array of microphones were planted on the ground. There's also a secondary array of microphones so we could take proper measurements. Very similar setup at Kennedy Space Center. And in this particular case, you don't want to put sonic booms on top of where people live. We call that the wall of humanity here on the far left. So there's a sonic boom flight where it's flying south. It creates a sonic boom. And we have some arrays also at the Kennedy Space Center site that will be heard at Kennedy Space Center, but not by where people live over to the east of this location. Of course, we want a lot of measurements to understand the atmosphere doing these. So this is just a short list of the sort of measurement, meteorological measurements that were made associated with each of the flights. We got a huge database. So this is one of the largest sonic boom data sets ever collected. We had 125 passes of aircraft, over 4,000 sonic booms recorded, and more than 95% of the signatures we recorded show the effects of atmospheric turbulence. Well, I'll focus on Trevor's work. We developed a numerical propagation model based on the augmented Polakov-Zabolotskaya-Kuznetsov propagation equation, also known as the KZK equation. And this requires very large computing resources. We'd like to thank very much NASA for letting us use their Pleiades system. We're assuming that the waves will propagate in the Z direction, which for us is along the ray direction. It's not up and down. And the particular modeling approach includes diffraction, thermoviscous absorption, nonlinearity, scalar turbulence, vector turbulence, and molecular relaxation. And those are all, each of these are small effects, but you need to include all of them in one model if you want to get an accurate idea of what the sonic boom waveforms will look like when they're measured on the ground. The measurement the simulation would not be correct unless we had a good turbulence model. So we have to model the turbulence in the atmosphere. We did that with a method of Wilson and Ostashev, and it's based on the variables you see right there. Some of the key pieces is that we wanted to make sure that we include the correct scales for atmospheric turbulence. So turbulence in the atmosphere, we used the modified von Karman spectral turbulence, including both shear terms and buoyancy terms. The method we used was the random Fourier modes method of Blanc-Bonneau to include the turbulence. So here we're showing three-dimensional cubes of the data. So the sonic boom would sort of move down through this. And on the left-hand side, we're seeing the scalar turbulence. On the right-hand side, we're seeing the vector turbulence. And you have to include both of these pieces to get a good model. To give you an idea, so if we're only looking in 2 dimensions, which was convenient for us, to save computational time a lot of the time. What we're able to do is actually to model the wave as it propagates down to the ground. So here the sonic boom wave is propagating through the turbulence you see right there. And by the time it gets to the ground, you can actually see that the waveform you had up the top has now been distorted slightly by propagating through the turbulence. Once we get output on the ground, we sample that. We assume the ground is rigid for simplicity, put in a 2.0 reflection factor. And if we take a plane in the ground, we can do slices through the plane, and that slices give us like what you would measure with a microphone, pressure versus here non-dimensional time. We then take those signatures and we look at them with a standard metric for sonic booms. We're using the perceived level. In this particular case, turns out PL is a good predictor of annoyance, so we're going to use that metric. There are a number of other metrics under consideration. I won't talk about those at this moment. But if you have a higher amplitude wave, you're going to get a higher PL. If you have a shorter ride time, you're going to get a higher PL. So there are lots of things that could make these louder. And to give you an exact idea for a particular simulation, here the black line is the undistorted waveform, as though there were no turbulence there at all. The one with the, you see how it peaked up, this red one, that's the one with the highest PL. The little blue in here, which is sort of smooth, that's one with the lowest PL, because you send a sonic boom in and it's random about whether you're going to get a higher or a lower value of the metric. Well, it turns out that our 2D algorithm worked very well. We actually made a lot of measurements of what the sonic boom waveforms would be from our database, and then we simulated them with our KZK Fourier numerical method. And you can see here the probability density of the distribution of the metrics around zero, either higher or lower than the baseline. Those match pretty well. So we feel this was really good result. We're very pleased that our simulation had a very similar distribution of the data as compared to what was actually measured. I will say that we did do some validation once we had the N waves running. Then we could actually run some examples of shaped signatures. So again, the validation we're doing right here is for N waves, which we have measurements for. We don't have measurements for the shaped waves because those aircraft are not flying yet. So we looked at a couple different things. The shape signature we looked at was the NASA Concept 25D concept. And we were able to show that there were distortions both for the N waves and the shaped waves, as well as you were able to get these kind of outputs. So for the N wave, here are the sort of distortions you see in the middle diagram. For the shaped waves, the amplitudes are lower, but you still do get the effects of the turbulence. You might also be interested in how this is affected by the strength of the turbulence. So for weaker turbulence, notice there is not quite as much movement from some, this is decibels relative to some nominal value. You can get an expression maybe plus or minus 5 dB, either for the N waves or the shaped waves. But when you have stronger turbulence, notice how this is, you get a much larger spread in the probability plot. One question we were also looking at is how often will the shaped signatures spike? So we were able to do those sort of simulations. The vertical axis is the friction velocity, which gives you the strength of the turbulence. So going vertical, it's how strong the turbulence is versus how far the wave is propagating here in meters. So for the N wave, you notice that as you go out to far distances or more turbulence, you're going to get a lot of changes of greater than, we're going to say, basically 9 PLDB. A factor of about 9 or 10 PLDB, people would consider to be about twice as loud. So this is these graphs are showing how often would you get an occurrence of a sonic boom to be twice as loud as it normally is. So for N waves, it's pretty strong, but notice here for the shaped waves, it's pretty rare that you ever get that to occur, even for stronger turbulence. We, of course, ran a number of statistical simulations in 3D. We could only run roughly 12 runs because the 3D simulations just take so long. They gave you 7.7 million waveforms, for example. We did this in 2 dimensions also, and we can run many more cases and still get a lot of waveforms. And so we wanted to do a comparison between 2 dimensions and 3 dimensions to see if the modeling made much of a difference. Turns out they make a little bit of a difference. It widens the PL distribution a little bit. You get a slight change from 3.0 standard deviation to 3.5, a minus 1.1 dB mean to a minus 1.6 dB mean. And so this tells us there are some differences going to 3 dimensions. But 2 dimensions often were enough for us. If you want high accuracy, you may need 3 dimensions. It does make a difference. So one of the 3-dimensional results I'd like to share with you today is this is a top-down view of PL metric relative to the nominal. So if everything on here were white, we'd be getting the nominal sonic boom signature. But you notice this is on the ground. We're looking at an area of about 400 by 400 meters on the ground. And you can see where it's blue, you're going to get a value of the sonic boom, which is a little lower. Where it's red, you get a little sonic boom, which is a little bit higher. So there are places where it's a little redder where you can have the sonic boom focusing. And again, plus or minus 9 dB is considered about twice as loud. If we make a slice through it, this is typically what you would get in an array. So if we made an array plot and we had an array of microphones, a linear array of microphones on the ground, you could see variations in the sonic boom level as you move along that. Well, remember, that's just a sample of what's really going on in multiple 2 dimensions if I look at an area on the ground. So this is the first time we'd ever seen this type of a plot before. One of the things I'm not going to spend the time on to give you all the details on, you can talk about what kind of arrays then, if you actually had microphone arrays on the ground, is it better to have a linear array or a cross array or a square array? We basically found out that the cross array or the linear array turned to be better. A simple grid array, you're just not sampling enough of the field is one of the outcomes. So a couple of the conclusions from the SonicBAT project are that there's a huge sonic boom database available now. We fully came up with simulations which we believe actually replicated the statistics of our actual measurements. Our results show that the shaped signatures of aircraft that are going to be built in the future, they will be less affected by the atmospheric turbulence than the N waves were. But having done this, we also realize that once we now have these 3-dimensional results, we can actually see how the atmospheric turbulence causes focusing on the ground, and we can make suggestions about how you would lay an array of microphones out on the ground to best sample that. Okay, so we want to thank everybody. We had a lot of people again who participated in this research, with real airplanes and real big computers being run. It was a fun project to work on. So I will just turn things back over and say I'd like to thank everybody for giving me the opportunity to tell you a little bit about this project. If you have specific questions for myself, here's my email. I'll be happy to, if I can't answer them, I'll try to refer you to the right people. And also I'd like to go back and thank Dr. Vigeant and Dr. Thompson for talking about some of the other things going on in propagation and radiation right now. So again, I'd like to thank everybody and hope you enjoy the rest of the CAV workshop this year. So thank you, everybody, and I hope everybody has a fantastic day. Thanks again, everybody. We'll see you later.